Hi, this is Dr. Bay, and here's Bugsy, and today we're going to go over the first part of addition reactions across alkenes. So, stay tuned.
Organic chemistry,
Taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy. Soaring through the sky, triumphantly we fly, give rise to the complexity of life. Living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Recall that alkenes can be made from E1 and E2 reactions, but we could add two groups across an alkene where the pi bond acts as a nucleophile to attack an electrophile. Addition reactions are when an electrophile, AB, is added across a pi bond. Today we're going to focus on 4 different addition reactions, and the 3 main questions that we're going to analyze for each reaction are 1. What are A and B? 2. What is the reaction's regioselectivity? And 3. What is the reaction's stereoselectivity? The first reaction is called hydrohalogenation, and it's the addition of a hydrogen and a halogen across a pi bond. For this reaction, A is a hydrogen as shown in red, and B is a halogen such as bromide, chloride, or iodide. In the following example, the first arrow is drawn starting from the middle of the pi bond going towards the hydrogen of HBr. And a second arrow is drawn from the HBr bond going towards bromine to form a new lone pair of electrons. This forms a carbocation intermediate where Br- acts as a nucleophile to attack the carbocation. And then we get our final product. Hydrohalogenation reactions are regioselective because the hydrogen adds on to the less substituted carbon, which is called Markovnikov's rule. How I remember this is that if a reaction follows this rule, that means the rich get richer, meaning the hydrogen will add to the side of the alkene with more hydrogens. This process occurs because the formation of a more stable carbocation is preferred. And if a new chiral center is formed after the addition, then a racemic mixture of enantiomers is formed because the nucleophile can attack both faces of the planar carbocation. The second reaction is called an acid-catalyzed hydration, which is the addition of water in the presence of an acid. For this reaction, A is a hydrogen, as shown in red, and B is an OH group. In the following example, the first arrow is drawn from the middle of the pi bond going towards the hydrogen of H3O+, and a second arrow is drawn from the HO bond going towards the oxygen atom to form a new lone pair of electrons. This forms a carbocation intermediate where water now acts as a nucleophile to attack the carbocation. Then another mole of water comes in to act as a base to deprotonate that extra hydrogen bonded to O, which will then give us our final neutral product. Acid-catalyzed hydration reactions are also regioselective and follow Markovnikov's rule, where the hydrogen will go on to the less substituted carbon of the alkene. And just like the last reaction, if a new chiral center is formed after the addition, then a racemic mixture of enantiomers is formed, because the nucleophile again can attack from either face of the planar carbocation. And the third reaction is halogenation, which is the addition of X2 across an alkene. For this reaction, both A and B are halogens like bromine or chlorine. In the following example, the first arrow is drawn starting from the middle of the pi bond, going towards one of the bromine atoms. And a second arrow is drawn from the Br-Br bond, going towards the second bromine atom to form a new lone pair of electrons. This forms what's called a bromonium ion intermediate. Then the bromine, or Br-, comes back and acts as a nucleophile. It doesn't matter which carbon of the bromonium ion Br- attacks, since you would get the same product either way. Halogenation is not regioselective since both A and B are the same. And in terms of stereochemistry, both halogens will add across the pi bond via anti-addition. This means that in the product, one halogen will be on a wedged bond, while the second halogen will be on a dashed bond. And halogenation also produces a racemic mixture of enantiomers. And lastly, the fourth reaction is called Halohydrin Formation, where one halogen and one OH or OR group are added across an alkene. For this reaction, A is a halogen and B is OH or OR. In the following example, the first arrow is drawn from the middle of the pi bond going towards one of the bromine atoms, and a second arrow is drawn from the Br-Br bond going towards the second bromine atom to form a new lone pair of electrons on Br. Again, this forms a bromonium ion intermediate that is triangle-shaped with bromine bonded to two bonds connected to it. Then the polar protic solvent, in this case water, comes in and acts as a nucleophile. The nucleophile will attack the more substituted carbon, and then the bromine that's part of the bromonium ion will open up. Then Br- comes back to deprotonate the extra hydrogen bonded to oxygen in order to get the final neutral product. And in terms of regiochemistry, the nucleophile will attack the more substituted carbon. And for stereochemistry, the halogen and OR or OH group will add via anti-addition as well. So in summary, we went over 4 addition reactions across alkenes. Both hydrohalogenation and acid-catalyzed hydration follow Markovnikov's rule, where the hydrogen will add to the less substituted carbon. And both halogenation and halohydrin formation occur via anti-addition.
Organic.